Yeah, sure.
Great. Just confirm with me when the live stream is started, no? Yeah.
Yeah, we are in live.
You're live now? Okay, great. Yeah. Okay. All right. Hello, everybody. Welcome. It's a Friday evening, late evening. So, uh, not surprising that we don't have many people here. Especially not surprising because this week we had two very long and very difficult lectures, I think, for you. I'm impressed that there are as many people, and thank you for sticking through the course all the way, especially sticking through this week, which is, I admit, quite tough. And it all, of course, follows from the fact that this course on ornithology is aimed at an academic audience. And so, one of the important things that academic researchers need to know is how to visualize and analyze data. And to be able to do that effectively, we have to know, to begin with, what are some fundamental aspects of the kind of data we collect, what are some properties of different kinds of data, and so on. So, if you're here today, I'm assuming you've managed to struggle through those two videos, and hopefully you have some questions for me as well. But what we'll do as usual, I think, is we'll start with the questions that have already come in through the Google form. And then, Nafisa, I don't know if you look to see if there are any questions in the discussion group, because I
Uh,
neglected to
there,
do that.
there's one
There's
question.
one. Okay, so
Yeah.
you could maybe read that out after
Yeah.
I tackle the ones in the form. And then, of course, the floor will be open to everybody else to ask questions here. Just type in the chat box as usual. So, I guess I'll get started then, and we'll try and address. There are only two questions that came in through the form, both by Akshay. And Akshay asks, can you explain this sentence about the equation for standard deviation? Quote, for each sample, deviation is added in the numerator, unquote. So, just to address this question, I don't know if Akshay is here. Is there an Akshay? I don't see an Akshay. Anyway, I think the question stems from the comment I made in the lecture that many because in this formula for standard deviation we see n or n minus 1 in the denominator, yeah, below the line. People think that as we add more data, that is, as n increases, we add more numbers, then the standard deviation decreases. But it doesn't do that for the same reason that even in the formula for the mean, if you remember, is the sum of x, so sum of all the numbers divided by n, which is how many numbers are there. So we have 10 numbers, then we sum up those 10 numbers, divide by 10. And if we add an 11th number, then we divide by 11. But of course, we've also added that 11th number in the numerator. So there's one more number in the numerator, plus the denominator has increased by 1. And that's why as we add data and we keep calculating the mean itself does not decrease. Even though the denominator is increasing, that's because the numerator is also increasing. So what happens as you add data, as you add your sample size, as you increase n, is that initially the mean bumps around a little bit, and then it stabilizes. That is, every additional sample that you take doesn't have much influence on the mean. And the same thing happens with the standard deviation. Because the standard deviation is you take the deviation from the mean, so x minus x bar, square that deviation, sum the square of deviations, and then divide it by n or n minus 1. So every time you're adding a sample, you're adding also one more squared deviation. And you're adding one number to the, you're increasing the denominator by 1. So similarly, just as for the mean, the standard deviation does not change systematically as you increase the sample size. More particularly, as many people assume, it does not decrease as you increase the sample size, even though n is in the denominator. Okay, I don't know how that made sense. One needs a whiteboard or a chalkboard, but hopefully that made sense to you. So the next question, also by Akshay, is what do you mean by true zeros? And I think Akshay is referring to the discussion about the different scales of measurement. And the idea of a true zero first came up in the lecture when we were talking about the interval scale. The interval scale is where every number, every difference in numbers means the same thing, but there is no true zero. So I gave the example of temperature in degrees Celsius. We have a 0 degrees Celsius, but it's an arbitrary zero. We have just decided that we'll call the freezing point of water 0. But we could have called the freezing point of alcohol 0, or we could have called anything else 0. And in Fahrenheit, of course, 0 does not correspond to the freezing point of water. So although the difference between 20 and 22 degrees Celsius is the same as the difference between 30 and 32 degrees Celsius, that is, the differences are consistent. Because there is no true zero, we can't take ratios. So in other words, it doesn't make sense to say that 20 degrees is twice as hot as 10 degrees. Because 0 is arbitrary. If we redefine 0 to something else, then that ratio would be different. It wouldn't be 2. 20 divided by 10 is 2. But on a different scale, like if we convert it to a Fahrenheit scale, it would be a different ratio. And that doesn't make sense. It doesn't make sense that if I convert my measurement scale to a different scale, then the ratio changes. That doesn't make sense at all. And the reason why it changes is because of the arbitrary zero. Now, if we had measured temperature on a Kelvin scale where there is a true zero, right? The true zero minus 273, where there is no temperature at all. That is there is no heat. Sorry, I should say there's no heat at all. And of course, that's a theoretical thing. In practice, I don't think we've been able to reach that. So that's an example where there is no true zero. Where we can convert it to true zero. But there are some other examples, like on a circular scale. On a circular scale where we get 0 and 360 are the same because the scale wraps around in a circle. Again, it doesn't make sense to say that to say that there is a fixed zero, because we can redefine it in any way. And so there are constraints. So we can take differences of angles and so on. But in that case, of course, we can say that 40 degrees is twice the size of the angle as 20 degrees, because that is actually unchanged by where we put the zero. It's not a major point because there are very few measurements on the interval scale, at least natural measurements. But just to contrast it with a ratio scale is, as you imply by the name, that you can take ratios of numbers that make sense where there is a true zero. So, for example, weight has a true zero. Weight of 0 is 0 grams. It weighs nothing. Or a height of 0, or length of 0 means 0 length, 0 height. And that's not arbitrary. That is an actual thing. It corresponds to something in the real world. And you can't have, typically in some of those situations, you can't have negatives. I can't have a negative length or a negative height, although I can have a negative growth. So a bit complicated when we start thinking about different kinds of measures, different kinds of metrics that we might use. But be very careful when you perform transformations of your numbers, especially when you do ratios. We have to first check whether the entity that you're measuring, or the scale in which you're measuring it, has a true zero. Only then should we be taking ratios. So that is what I meant by true zero, Akshay, if you're there. Okay, I'll come to let's see if there are any questions about this or comments about this. And if there are other questions not related to these 2 points, then we'll take them a little bit later. How often does the population mean change? When the zero is not available, can we use our control observation? Control observation, like in an experiment, we should let's not call it a zero, let's call it a comparison. So there's always a comparison. And then the question always arises, Gaurav, is what is the appropriate comparison? So for example, if I do an experiment and I add fertilizer, let's say, to some plots of grass, and I see how fast grass grows, and I compare the biomass, that is the total weight of grass in the control versus the total weight of grass in the experimental units where I've added fertilizer compared to where I've not added fertilizer. And let's say the total mass here is on the control is 300 grams, and the total mass elsewhere is 400 grams in the treatment. So the tricky thing that always arises is, do I take the difference between the two? So I say there was an increase of 100 grams or a change in 100 grams, or do I take the ratio, which is Now, to say that 400 is 33% larger than 300. So is that the relevant biological measurement, or is the 100 grams? So this is the absolute difference, or is it the proportionate difference? And that is a topic we won't get into right now, but I just want to, because it's complicated and there's no straightforward answer. But I want you to think about this when we're comparing things. When we compare, even in our everyday lives, we compare GDP of the country, or if we compare whether has the price gone up by 10 rupees, or is that price gone up by 200%? What is the appropriate measure with which to look at these comparisons? Something for you to think about. Nafisa, if you have that question from the discussion group, could you just read it out?
I've pasted it here.
Oh, you have. So, that's the question from the Bootstrap.
Yeah, that's the only question.
That's a nice question. If you guys are reading it, if we start with the assumption, the original sample set is a true representation of the population, which is, it's not quite the assumption of Bootstrap, but let's go with that. Can't the mean we calculate be assumed to be the mean as a true mean as well? How can repeated sampling help give us the real mean of the population? So the answer to this is that the repeated sampling does not help give the real mean. It gives us a sense of how different our estimated mean might be from the real mean. We have no direct access to the true mean or the real mean of the population. So all we have is the sample. And if we can assume here, this is not quite the right phrasing in the question, that the sample is a true representation. It's not a true representation. It is shall we call it an unbiased representation. So if it's not biased, that we are consistently measuring something low or consistently measuring something high, if it is representative, then even when you take a representative sample of the population, just by chance, the mean that you get from that will not be equal to the true mean. And you can think about it. If I have in a class of 20 students, and I want to understand the mean height of those students, right? Now, imagine I can only measure 2 students at a time. So I take 2 students and average their height, correct? Now, it's very unlikely that the average height of those 2 students will be identical to the average height of all 20 students, which is my population, right? So I don't assume that my sample mean, the mean of those 2 students, is the same as the population mean. In fact, that's the whole thing of statistics. We are not assuming, we cannot assume that. But what we want to understand is how far might this sample mean be from the population mean. But we have some confidence that it's pretty close, or do we have low confidence that it's pretty close, right? And you can imagine this by taking 2 students over and over again and calculating their means. And in that case, you know the true mean. And you can see that the mean of 2 students is going to be quite far sometimes from the population mean. So we're not assuming that it's a true representation. We are assuming that it is a random or a representative sample from the population. Given that it's a representative sample, even then we know that the means are not going to match, although the sample mean is our best guess for the population mean. We want to understand how closely or not closely it might match the population mean. And by the way, that is the case with all statistics. So there are other, if we take the normal distribution type statistics and calculate precision in another way, calculate the confidence interval in another way, again, we only have the sample that we have, right? There's nothing else. There's no other information we have. The only information we have comes from the sample. It's not as though we can create information out of nothing, or we can create information out of something other than the sample. So we have to make the best with what we have, and that's actually the literal meaning of Bootstrap as well. I'll just look at the earlier questions as well. How often does the population mean change over the course of time geographically? That's a really interesting question, Gaurav. In fact, in the branch of statistics that we have been dealing right now, or not the branch, but rather it's a approach to statistics, or even a philosophy of statistics. This is called frequentist statistics. You don't have to remember the name. But in that way of looking at statistics, the mean of the population is fixed. right? There is some true mean. And through sampling, we are trying to get at that true mean. So the mean is fixed, but the sample mean that we get is a random variable. It changes depending on which sample exactly we happen to get at that time. But there's another way of thinking about statistics where we say the only thing that is fixed is the sample. That's because that's the only thing that we have. We only have a sample. And actually, what is varying at random, or we can think of it as random, is the population mean. Partly for what you're saying, the population mean doesn't remain static, right? Because the populations themselves are not static. The populations fluctuate over time. Today, there are 1,353 peafowl, but this evening, 3 of them get killed by a leopard. So there are 3 less, right? And a week later, there's some that grow into the population or immigrate from somewhere else, and so it keeps changing. So in any case, not to complicate things, and again, you don't have to remember this for this particular course, but the practice of extracting meaning from data, of making larger generalizations from our data is a complicated and layered, nuanced matter. And of course, in these lectures, tough and quantitative and number heavy, although they may have been, we're only really beginning with scratching the surface. Sorry to say. So more literally to answer your question, Gaurav, sure. I mean, every year the mean length will be different. If there is some effect of, let's say, an environment where in some wet years, perhaps, people are better fed, and if you're better fed, you are able to grow a longer tail, and maybe wet years, or if the preceding year was wet, perhaps, then you can grow a longer tail this year, and if the preceding year was dry, you can grow a shorter tail. So there are all kinds of things that would change things, and similarly, if you think of evolutionary forces, they may actually be a directional change over time, or with global warming and things like that. So you do expect things to change from year to year. And another question from Gaurav is, can we estimate the population mean for samples outside our collection area? So I think these 2 sentences you said slightly different things, Gaurav. So suppose you sample peacocks in Delhi and then extrapolate. I wouldn't say predict, but we extrapolate tail length for other individuals across. So we're extrapolating outside our sample. And extrapolation in statistics is always very tricky. And unless you have some other good reasons to expect that extrapolation to be valid. So, for example, if you measure Delhi peafowl and extrapolate to peafowl in Kerala, for example, with a very different climate and different habitat, anybody who knows natural history or bird biology would say, this is pretty risky. But you don't know how right or wrong you are unless you actually measure the peafowl in Kerala or wherever, Assam, wherever else far away from Delhi. So you can extrapolate all you like, but you don't know whether you're right or wrong. And because you don't know whether you're right or wrong, it's a very risky thing to do. If you sample, let's say, in Delhi and in Trivandrum and in Guwahati, I'm using those place names as markers for the geography. Then you could argue, okay, I've sampled across the country, and then I'd be able to say something about peafowl across the country or peafowl in these 3 states or whatever else. But there you actually have information. In the absence of information, extrapolating is frowned upon, shall we say. I'm just going chronologically down the questions. Why do we say the narrower the interval, the more precise the data? So the more precise in the sense that we are able to trap our estimate of the true population mean in a narrow interval. So if I say that the average exam score of a set of students was 25 plus or minus 2 marks, right? I'm taking a sample of a larger set. Then I have a confidence that the true mean, which I don't know, the true mean lies between 23 and 27 marks, okay, which is plus or minus 2 marks, 4 marks range. If it's 25 plus or minus 5, then it's 20 to 30. So I don't know where the true mean is. It's somewhere between 20 and 30 is my guess. And the other case is somewhere between 23 and 27, right? So between 23 and 27, I hope you would agree, is a narrower range. And therefore, I have more in statistical parlance, a more precise estimate of where the true mean might be. In both cases, my best guess is 25. But in the first case, I can exclude with some confidence anything outside 23 to 27. But in the second case, I can't exclude, 20 to 20, 30. So I'm less sure, I'm less precise in my. So that's why the narrower the confidence interval, the more precise our estimate is. I'm hoping that makes sense. Archana, you wanted to add something?
No, I'm still trying to understand it. So let's say I have, sorry, I don't know if I'm going to make sense. 95% at 95% confidence interval, I have a larger data range, right?
Larger than?
Larger than a 90% confidence interval, for example.
Yes, yes.
So now if I'm comparing the two, then 95% is actually should ideally be a more precise, I mean, closer to, should it not? Or am I understanding this wrong?
No, so Archana, yeah, I can see where you're coming from. The comparison is not between different this is called the coverage of the confidence interval. Sorry, it's a bit technical, but so the coverage can be 95%, it can be 90%, it can be 50%, right?
Okay.
We know that if we change the coverage criterion, then the interval will become larger or smaller or whatever. So for example, if I have a 50% confidence interval, then the interval will be small. If it's 90%, it will be larger, 95% will be even larger, 99% will be even larger. That's because I have different stringency in what I expect from that what I want to be able to say. So for example, a 50% confidence interval, I'm going to say this in a casual sense, it's not technically correct, but casually to understand. If it's a 50% confidence interval, then I'm saying, let's say it's 20 to 30. So then I say that there's a 50-50 chance that the true mean lies between 20 and 30 versus outside that. There's a so 50% chance that it's there in that range, 50% chance is outside. But so that's okay if I want to, if I'm okay with that, 50-50, okay? But if I want to say there's a 19 out of 20 chance, which is 95%, that it's within that range, yeah, then I want to leave less space for the mean to be outside that range. And for the same amount of data and the same standard error and all that kind of thing, I still have the same information. The only way I can make that is to increase it. So let's say to 5 to 45 or whatever the range would be. So then I can say between 5 and 45, I'm 19 out of 20 times sure that it's between that range. The less stringency I want to I need to impose on this, the narrower it will become. So that's not the comparison to make. We know that if you have a 50%, it will be narrower, 90% will be that's okay. The comparison to make is the same stringency, let's say 95%, across two different data sets or across two different measures. Right? What will under what situations will the same 95% coverage, will it be smaller or larger? And that's where, not comparing across 95% and 50%, that we already know it goes in that. That's just a fact of life in a sense. But then to ask ourselves, okay, how can I narrow down the 95% confidence interval? What do I need to do? And I discussed in the lecture, there are two things that affect how wide any particular confidence interval, let's say 95%. One is how variable the population is in the first place. So if the population is very uniform, then that any confidence interval will be narrow. And the second is how much sample, what's your sample size? So as the variation in the population becomes smaller and as your sample size becomes larger, I can make the 95% confidence interval narrower and narrower and narrower. So I've trapped the true mean within a narrower interval. But if I, for example, don't compensate for very variable population, if I don't compensate by increasing my sample size, then my confidence interval will be very large. And that may not suit my purpose. It may not help to say that, the growth rate of trees is, per year is 0% to 200%. it's a huge range. It doesn't help me at all. Doesn't tell me anything.
Right.
I really want something more informative than that.
Yes. Okay, thank you. That helped.
Thanks, Archana. And the question is, when is 50% confidence used? So the tradition in our field, in ecology, generally in organismal biology, is to use a 95% confidence interval. But there's a well-respected statistician who's argued quite strongly that a 50% confidence interval makes more sense, not just because it's a narrow interval, right? Because that people always like narrow intervals. The question is, what does that mean? It's because he argues it's more intuitive to imagine that it's like a coin flip whether the true mean is inside this interval versus outside. We are more comfortable as humans. We are able to understand better when something is like 50-50 chance. And what he says is that by using the 95% cutoff, actually what happens is most people, including trained scientists, tend to forget that there's actually a 5%, there's a non-zero chance, there's a 5% chance the true mean is outside that. So the way that many people tend to interpret a 95% confidence interval is that this is the 100% confidence. That is, the true mean is somewhere between these two, right? It is going to be between here and here, but that's not the interpretation. That's not the case. It's only got a 19 out of 20 chance. There is still a 5% chance outside. So if I do 20 analyses and I come up with 20 of these confidence intervals, in one of them, on average, that confidence interval will not contain the true mean. The true mean will be outside, and I'll be completely wrong. You know what I mean?
Right. Yes.
And so, to make the fact that this is actually a probabilistic statement, make that particularly clear, I think he's arguing that if we do 50-50, then people will know very clearly that there is a chance, 50% chance, that actually the true mean is not here. Anyway, that proposal has not been taken up, and people still go with the 95%. But it's just something to mention, I think, to you to also to understand that these conventions, like 95% or whatever, are conventions only. There's no particular hard and fast rule or reason for it to be 95 or 99 or 90 or 50. It's only a convention. And I think people often make the error in thinking that a lot of science, including the analysis and statistics, is somehow like a recipe book, like fixed. But actually, there are many judgments that an analyst would make. And so what comes out at the end of an analysis and the conclusion, and this is a lesson generally for all of you, for when you read the conclusions of scientific papers, there is a considerable amount of subjectivity in it. There's a considerable amount of room for the researcher to bring their own reasoning and their own decisions, even to something that we consider objective and number-based, like statistics. And this is a general thing about science overall, but I'm making the narrower point that even where you think, oh, it's just maths, I just calculate and whatever comes out, comes out. But actually, that's not entirely the case. So we can be skeptical, or we can interrogate results from science, including we can interrogate the particular decisions that were taken in the study design, the particular decisions that were taken in the data collection, and the particular set of decisions taken in the data analysis, all of which have various amounts of decision making and subjectivity built into them. So don't ever imagine that science we pretend is an objective pursuit where there is no personal input, but of course it's a human pursuit and there's always human personal input into it.
Right. Thank you.
Yeah, sure. That was a bit of a tangent, but
no, but it was interesting.
Cool. I think, okay, so now we have something set. Okay, Gaurav again. Are we zooming? No, really. No, we do assume in frequentist, in our band of statistics, we do assume, Gaurav, that there is a true mean. There is a true mean out there. And if we were able to measure every single possible sampling unit, which is a sampling frame or the population, if we were able to measure the population, we would be able to access that true mean. So for example, I used the example of exams earlier, which is not a good example, because in the case of, let's say, your CBSE school 10th class exams, we know the true mean, right? Because we have the scores of every single child who took that exam. So we know the true mean. There's no debate about it. And that's why we can actually say that, let's say girls scored 73.2% and boys scored 72.1%. So girls scored on average 1 percentage point higher than boys. We can make that statement because we have the full population, and there is no doubt about it. However, if we had only a sample from that population, and from that sample we wanted to make some conclusion about whether and how much girls and boys differed in their percentage that they get, then we would have to be much more cautious, because any sample comes with a precision. And the precision might be, girls scored 73.2%, but it's plus or minus 1%. So 72 to 74, and boys scored between 71 and 73. And we can see there's quite a bit of overlap. So how confident are we that actually there were more? And our best guess still is that girls scored 1 percentage point more than boys, but that comes with some uncertainty. So when we have the full population, sure, go ahead. There's no uncertainty. You can make confident statements. But that's a very, very rare occurrence where we have, especially in ornithology or ecological sciences, we typically don't. So what we're doing is we're trying to make some conclusion about that true mean without having direct access to that true mean. The only access we have is through the sample. So we don't make the hypothesis that the sample and population mean are the same, because we have no means of testing whether it is true. Your last word. There's no way to test whether that's true because there's no other information available to us. Isn't 95% CI better than 90? Well, better is how you mean the word better. So 95% CI is better because it has a higher chance to contain the population mean, yes, but it's also wider. So 95% chance within here, 5% chance outside, versus 90% chance within here versus 10% chance out there. Or you could say 99% chance within the range and 1% out there. It will change. 99% will be very broad, 95 will be narrower, 90 will be narrower, 50 will be narrowest. It doesn't really matter really, so long as you know what that means. Now, sometimes it matters, especially if some decision has to be based on this. So for example, if you are a manager, a population of like a forest department person or somebody who's managing the trees in a place, or I don't know if I gave this example where there is some action that is triggered based on some assessment. Like suppose if the birth rate of tigers falls below some threshold in a particular year, let's say there is a policy that some action is triggered. That let's say the cubs are fed supplementary or something like that to ensure that the survival rate of the cubs is higher. Then there is an actual consequence. So then we have to figure out, okay, whatever the threshold is, we have to figure out how confident are we that the situation on the ground is above that threshold or below that threshold. So there we have to really bring all our kind of faculties to that, to try and figure out what is our confidence that the whatever we're measuring, birth rates, is comfortably above that threshold or is alarmingly below that threshold. And there we can get into debates about then should the confidence interval in our birth rate be 99% or 95% and so on and so forth. And then we also have to remember that because there's uncertainty, we are also making our decision in the face of that uncertainty. And so we have to think about what are the consequences if the situation on the ground is actually not what my best guess is. Suppose my best guess is that the birth rate is below the threshold, but there's a 5% chance that I'm wrong and it's actually above the threshold. So maybe it's okay to be conservative and say that it doesn't matter even if there's a 5% chance that actually things are fine. Supplementary feeding the cubs is still okay. I'd much rather take the risk of feeding the cubs when it's not necessary than not feeding the cubs when it is necessary. Do you understand what I mean? So there are different consequences for different decisions. Now, that's in the context of some decision about some action on the ground. And you can think about how important it is to understand on what evidence that decision is being taken and what are the consequences of taking that decision if the actual situation is not is the opposite. But most research, at least pure research, there is actually no consequence if the decision is wrong. If I say, oh, my mean is between 20 and 30, but actually you're wrong and the mean is outside that range at 15, in pure research at least, there's no real consequence of it because nobody is acting on that information. So whether or not that makes pure research, well, I don't know what that makes pure research, but certainly if you're doing let me stick to one conclusion, which is clear, that is, if you're doing applied research, whether if there are going to be consequences of what you find, on ground actions that are taken or not taken, depending on what you find, then these assessments and the honest reporting of uncertainties are particularly important. And so it's not surprising that very often in applied research, a lot of the development of these techniques and this understanding has been driven by applied researchers because there are such severe consequences if you get things wrong. I tend to wander off on these answers. I'm very sorry. Would it depend on how smooth the distribution curve? So no, Gaurav, because remember from the central limit theorem, we're not talking about the distribution, frequency distribution of the actual data, whether it's marks or whether it's heights or whatever else. We're talking about the frequency distribution of the possible means you could have gotten from your different samples. So I take a sample from a population of 20 and I get a mean. If I had taken a different sample of 20, how different would that mean have been? And a different sample of 20 and a different sample of 20. The distributions of the means of the samples, because of the central limit theorem, are mostly going to be bell-shaped and roughly normal. So they're not going to be skewed, although the distribution of the original data may be skewed. But we don't care about the distribution of original data because we're not making any conclusion about the original data. We are making conclusions about the mean of our sample and how far away or near the mean of that sample may be to the mean of the population. So it's the distribution of those hypothetical sample means that is what is important to us. I hope that makes sense. So remember, when the central limit theorem applies, and the whole reason we use normal theory based statistics is nothing to do with the distribution of the individual data points. It has to do with the theoretical distribution of the means of the samples that we take, which is very likely to be normal or near normal. Okay, heavy stuff, huh? I think I've said some words at least about all the questions here. Are there any others? Please do so. It's difficult stuff. I'm quite aware that at least the way that I teach it and some others, colleagues and all teach, unfortunately, there isn't any textbook that that covers this vast range of things, from asking questions to research design to analysis, in the way that I really prefer it to be. So that's why I've not really assigned I think there in the additional reading, there are a couple links to a couple of textbooks. So unfortunately, those textbooks are, to my mind, not quite, don't treat the subject matter the way it should be. So, but I'm working on some, written material. So hopefully this doesn't help you guys, but hopefully by the next edition of this NPTEL Ornithology course next year, there'll be some actual textual material that you can follow along together with the videos. So hopefully that will help the next batch. Good. Thank you, Ramkumar. I'll wait for another 30 seconds or so, but if there aren't any questions, further questions, we can wrap up a bit early. Nafisa, nothing else, no, pending from the different channels?
No.
Okay. And maybe one more thing to just mention is that, we unfortunately the textbooks, one of the reasons why I don't like the existing ones is that there are very few or none that integrate all aspects of research. So the thing is that most textbooks teach statistics and data analysis as a separate topic. So there'll be a textbook of statistics. But I feel very strongly that you cannot understand and you cannot apply your statistical analysis without reference to the way in which the study was designed, and you can't design the study without reference to the question that was asked in the first place. And then, of course, the results of your statistical analysis needs to feed back to that question. So I feel that entire loop of question, study design, data collection, data analysis, inference back to question, that entire circle, which I've depicted repeatedly in my lectures, that has to be treated as one whole. And unfortunately, the textbooks don't do that. They slice that up. They slice it up into different parts, and there's a textbook for this and a textbook for that, and things like that. And that to me is very unsatisfying. Okay, clinical research, clinicians of 10 samples of rare disease. Do they use statistics but also prefer the medical method? This is a tricky question. I don't quite know what clinicians do. I know that sometimes when patterns are very clear, and especially if there are decisions to be made, consequences, then people make those decisions based on very few samples. Now, I'll give you an example of this. Back in the early mid-2000s, when people still didn't know why vultures were declining. There were various ideas about why vultures did not have food, not have nesting sites, maybe some disease. Each of those was investigated and couldn't explain why vultures were declining. And then finally, there was some evidence came to light that it might be poisoning from this cattle, this drug that's given to cattle, diclofenac. And if the livestock, whether it's goat or cow, whatever, dies within 3 days of being given diclofenac, and if vultures feed on it, then the diclofenac has not yet been metabolized and broken down in the body, and then that can affect vultures bad. So there were some some symptoms that seem to be consistent, the internal organs and so on, of diclofenac poisoning. But of course, as you know, the gold standard, whether it's COVID vaccines or whatever, gold standard is a clinical trial. So what does a clinical trial mean in this case? It means to feed the vultures meat that has diclofenac and then see what happens. Now, as you can imagine, this is a pretty serious thing. Vultures already declined up to 10% or 5% of their population. How can we justify, if we think that this is killing them, how can we justify killing vultures in this way? But still, it's the gold standard. To find out whether diclofenac is doing it or anything, we have to do that. So, if I remember correctly, they managed to do this on vultures that had been kept in captivity in Europe. So these are European, in European zoos, I forget where exactly. Same species as ours, but the experiment was done there. And what they did is they had some controls where they fed some neutral substance, and then they had this experiment, just like we do in a proper experiment. And so they gave it to the first vulture. So rather than giving 10 vultures all at one go, they first gave it to one vulture, and within a day or day and a half, that vulture was dead. Then they give it to the next vulture, and within a day and a half, that vulture was dead. And when doing the autopsy and so on, they also had the same kind of symptoms of gout and uric acid deposition and so on in internal organs. And the third vulture, within 2 days, the third vulture was dead. So at this point, although normally we would say sample size of 3 is insufficient for any experiment, we should do 30 or 20 or something like that. At this point, the researchers felt that the outcome was so stark and so clear that it would be silly to simply continue the experiment just because some statistician said at some point that we need to have 20 or 30. It was so clear. So there they use that very stark outcome, very clear outcome, to say that there is more harm in continuing this experiment than in stopping now, even if, you could argue, 3 vultures could die by chance. But anyway, that was a kind of a discussion and decision that was made at that time. Yes,
Can
please.
I answer this question as a clinician?
Yes.
I'm a retired gynecologist.
Yes.
So evidence-based medicine is the best. I'll answer it in 3 sentences. Evidence-based medicine is dependent on the best research, which is a randomized control trial, the physician's experience, and how much the patient also can afford, or whatever the situation where the hospital is in. So for randomized control trial, you can try a drug. Now the vultures died, so they had to stop the trial at that point.
Yeah.
So for rare diseases, to answer the question that this person asked, like when COVID came or whatever, for rare diseases, we have to believe case reports and case series for rare diseases.
Yes.
And we're going to test a drug and we do it the placebo, we'll do randomized control trial.
Yes. Yes.
But the student who asked, so for observation studies, for causation, you have to do an observation study. For a drug, you have to do a randomized control trial. And physicians, for rare diseases, they have only that case series to, that's why, remember, for COVID, they used remdesivir, then they didn't use remdesivir. Sorry for I felt like saying it because I'm a retired gynecologist.
Yes. Thank you very
and
much.
Also, a clinician taught me statistics when I was 57 years old. And just like you, he was teaching statistics as the statistics department teachers. I never understood. So an ENT surgeon taught me. That's why I want to tell you, Suhail, because I saw you in Bangalore. I met you once when you spoke, that you're like that teacher who taught me, and it's very nice, but it's so tough that even if you read again and again and again, like 95% confidence interval, I've been hearing for 30 years when we started measuring hyperparietal diameter of the fetal head on ultrasound.
Yeah.
So at least when everyone's talking about that, I'm understanding, but I'm still stuck on sample size and regression. But I will work on it because you inspired me, and I want to say thank you.
That's wonderful. Thank you for that. I did also want to point to, most of you are beyond that stage, but I did want to point out, this is especially for those still in school or perhaps in college, that for better or for worse, most modern science, including social science, not just biology, not just ecology, is very quantitative. It deals with numbers a lot. And the unfortunate reality is in our education system, those who have an interest in social science or interest in biology are discouraged from dealing with numbers and maths after class 10. Not that maths is taught in a very interesting way in most places, but nevertheless, I think we do ourselves a disservice if we are interested in biology or social science, and therefore the education system removes maths from our curriculum. Many schools don't even allow biology and maths to be taken together in 11th and 12th. And this is partly, why we come to this stage and we struggle with these things, because we're not used to thinking quantitatively, we're not used to thinking in terms of numbers. We've not done some basic programming and stuff like that allow us to experiment with this sort of thing. So anyway, for yourselves, if it's late, that's okay. If you're later in your life in this, if you're already into research, master's, PhD, beyond, then I think the biggest favor you can do yourself is to immerse yourselves a little more in numbers, because the more intuition we have about numbers, where they come from, how they behave, how they can inform us about what we want to know, and how they can mislead us, because as you know, statistics can mislead you. There's a very famous quote that says there are three kinds of lies. So 3 kinds of lies. There's lies, damn lies, and statistics. And of course, that comes from the particular observation that people can hide behind numbers, they can obfuscate behind numbers, they can lie with numbers. So we need to, as researchers, but of course as citizens as well, we need to arm ourselves with enough quantitative understanding. It's called numeracy as a parallel to literacy. Literacy, we all agree, is very important, but numeracy is something that we don't think about. And that has to do with an intuition as well of numbers, not just the formal, I can do my times tables and so on, but also an intuition. And the only way you get an intuition is not, you're not born with it, but you have to immerse yourself in that world. So, for you or others, if people come to you and say, I want to do biology, ecology, I want to drop maths, please encourage them not to do so. And there's lots of amazing resources on YouTube and so on, where you can learn fundamental mathematical concepts in a way that was never accessible to me in the classroom, certainly. So, the digital world now is full of amazing pedagogy and ways to immerse yourself in numbers. Yeah. Okay, I've spoken a lot. I know we have a few minutes left, but with Nafisa's permission, maybe we can draw this to a close.
Yeah, yeah, sure, sure.
Yeah.
Thank you
Okay.
so much for
Great.
your.
Thank you everybody for a lively session. When I first joined, I thought, oh, this is going to be a short one. But it's a little not, it turned out to be more interesting. Just one last one here. Overall, is ecology a game of percentages and average? Is ecology a game of percentage and average? No, ecology, of course, is not a game of ecology. Is the interaction, how individual living beings make their living and how they interact with others, and how all that emerges as populations and population change and communities of species and so on. So that's ecology. But our understanding of ecology, our access to the world of ecology, when we want to understand, interrogate, and access, that mostly is done through a game of numbers. And that's what I'm interpreting from your game of percentage and average is a game of numbers. We need to translate, typically we need to translate, because any complex system like ecology, we can't simply verbally describe it. And even if we can verbally describe it, when we want to analyze it, it's very hard to do so verbally or impossible. So we need to somehow distill some essential features, important features, into numerical measurements, into metrics that we can measure, we can compare, we can track over time, and so on. So it's, I think, inevitable that numbers are our window into the world of ecology. Although I think the reading between the lines, the numbers themselves are not the ecology. They are only our window into ecology, and we shouldn't also fall in love too much with the numbers. Ultimately, they're living breathing beings out there. They're interacting. That's the ecology happening. The numbers are just our language of talking about it in some sense. Okay, thank you all, and see you later. All the best. I'm not going to be in a live session with you again, I think. But all the best for the last couple of weeks of the course. And of course, for those of you who are taking the final exam, all the best for that as well. And please do remember to give feedback during the feedback forms and so on.
Thank you.
Sushila, it is a basic course, I'm afraid. From an academic perspective, from a research perspective, it's pretty basic. If you are not in an academic or a researcher, then it can look pretty advanced. But believe me, we are only beginning to scratch the surface. Thanks a lot and good night. Have a good weekend. Bye, everybody.
Thank you so much. Good night.